Hi everyone, I am Rishi Panchal. Today we're diving into one of the most revolutionary cost curves in energy history, the dramatic price drop in lithium-ion batteries, particularly the LFP chemistry that's driving massive changes in both electric vehicles and utility-scale energy storage. According to Bloomberg, in 2024, lithium-ion battery pack prices fell an incredible 20% to just $115 per kilowatt hour, the largest price drop since 2017. At these prices, Chinese batteries are becoming economically irresistible, even with significant import tariffs. What's driving this revolution? Let's explore the fascinating world of LFP batteries and how China has engineered solutions to what were once thought to be fundamental limitations. Let's start with understanding lithium-ion battery basics. Every battery has two electrodes, the cathode and the anode. The anode is typically made of graphite, while the cathode represents over 70% of the battery's value and is how we distinguish between different battery types. There are three major lithium-ion battery chemistries in use today: NMC, nickel manganese cobalt, a ternary battery with energy density between 250 to 320 watt-hours per kilogram; NCA, nickel cobalt aluminum, another ternary option with energy density between 230 to 260 watt-hours per kilogram; LFP, lithium iron phosphate, a dual chemistry cathode battery with energy density between 90 to 160 watt-hours per kilogram. The ternary batteries offer higher energy density, meaning they can store more energy in the same size and weight. This allows EVs to potentially travel further on a single charge. However, this comes with significant drawbacks. They require rare, expensive materials like nickel and cobalt. They present higher thermal risks, potentially leading to fires through thermal runaway. LFP batteries, on the other hand, use abundant, cheaper materials, iron and phosphorus, have better longevity, maintaining their capacity over more charge cycles, offer significantly improved safety with lower thermal runaway risks, come with a substantial cost advantage. It's essentially a trade-off triangle between performance, cost, and safety. Ternary batteries prioritize performance, while LFPs excel in cost and safety. In the early days of lithium-ion batteries, the first chemistry was lithium cobalt oxide, LCO, which used nearly a kilogram of cobalt for each kilowatt-hour of energy capacity. This was problematic as cobalt mining in the Democratic Republic of Congo raised economic, moral, and environmental concerns. This led to the rise of ternary battery chemistries, which still used cobalt but in much smaller amounts. In the 2010s, pioneering Western EVs like the Chevrolet Volt, Nissan Leaf, and Tesla Model S all used these ternary chemistries. Meanwhile, China was taking a different path. Early Chinese EV makers adopted LFP batteries, particularly for buses, driven by government policies like the Thousands of Vehicles, Tens of Cities initiative launched in 2009. This program provided subsidies for municipal governments to purchase electric public service fleets. Companies like BYD became early LFP pioneers due to cost and safety considerations. For the first few years, LFP dominated the Chinese EV industry. Around late 2016, the Chinese government began changing its subsidy policies to encourage more consumer-friendly EVs. The new policies linked subsidies to factors like energy density, driving range, charging speed, and fuel savings. EVs with ranges below 150 kilometers received no subsidies at all. This policy shift favored ternary batteries, which could deliver higher energy density in longer ranges. Even longtime LFP champions like BYD began switching to ternary batteries for models like the Tang 100, Song EV300, and Keen EV300. By mid-2019, ternary batteries had captured about 70% of the market, with LFPs falling to 30% or even lower in some quarters. Two major developments breathed new life into LFP technology. First, in June 2019, the Chinese government signaled it would gradually withdraw the EV cash subsidies. This was partly due to the scale of subsidies becoming significant and reports of subsidy cheating with fake customers or vehicle registrations. The subsidy reduction was aggressive, an immediate 50% cut in mid-2019, with more reductions planned for subsequent years. This leveled the cost playing field, prompting many EV makers to switch back to LFP. Second, and perhaps more importantly, LFP manufacturers began developing innovative technologies to overcome the chemistry's fundamental weaknesses. In March 2020, BYD introduced the game-changing Blade battery, which debuted in their flagship Han sedan a few months later. To understand why this was revolutionary, we need to examine the three manufacturing levels of EV batteries. Cells, the fundamental building blocks containing the cathode, anode, and electrolyte. Modules, groups of cells bundled together for easier handling. Packs, the final battery assembly that goes into vehicles. Traditional battery manufacturers grouped cells into modules, which were then assembled into packs. BYD's breakthrough was to skip the module level entirely, creating a cell-to-pack CTP architecture that placed cells directly into the battery pack. To maintain structural integrity, BYD reimagined the prismatic cell form factor, creating an ultra-thin, very long cell that spans the width of the battery pack, hence the name Blade. This innovative approach delivered remarkable results. The extended range version of the 2020 Han EV achieved a range of 605 kilometers using LFP chemistry, comparable to premium ternary-powered EVs like the Tesla Model 3, 668 kilometers, and Xpeng P7, 706 kilometers. The key difference? The Han achieved this with much cheaper LFP batteries and at a significantly lower price point, between 210,000 to 258,000 RMB versus 270,000 to 330,000 RMB for the ternary-powered competitors. The CTP approach gives LFP battery packs approximately 85% of the energy density of conventional NMC batteries. Interestingly, ternary batteries struggle to adopt CTP due to their higher operating temperatures. Other major Chinese battery makers quickly adopted similar concepts. CATL, for instance, developed their own CTP technology for their Keelan battery pack. By 2021, LFP battery volumes overtook NMC, and by 2023, they accounted for nearly 70% of EV battery installations in China. While NMC batteries still offer better energy density, they're now primarily used for premium, high-performance vehicles like the Xiaomi SU7's Max and Ultra versions. Another critical factor in China's LFP dominance involves patents. The original lithium-ion battery structure and LFP cathode were discovered and patented by American scientist and Nobel Prize winner Dr. John Goodenough. However, his LFP design wasn't commercially viable due to poor electrical conductivity. Later innovations in carbon coating and process technologies made LFP commercially competitive. These advances were patented by researchers at universities and public entities in Canada and Europe, with the patents consolidated under a single Swiss entity managing global licensing. According to the International Energy Agency, an arrangement in the 2000s where 2010s allowed Chinese battery makers to use these LFP patents for free, but only in their local markets. All other countries had to negotiate and pay licensing fees. This patent shield enabled Chinese manufacturers to develop expertise in LFP, while the rest of the world's battery makers pursued other chemistries to avoid licensing issues. These patents finally expired in 2022, allowing foreign battery makers to use LFP chemistry without licensing concerns. However, anyone entering the market now faces a massive disadvantage, as Chinese manufacturers have spent years building immense supply chain proficiency, with economies of scale, materials sourcing expertise, and technological innovations like cell-to-pack designs. Until 2021, BYD practiced vertical integration, keeping its batteries exclusively for BYD vehicles. This approach was necessary during the technology's early development, but allowed other manufacturers like CATL and LG Energy Solution to establish themselves in the market. In 2021, BYD began selling its Blade batteries to third-party automakers like Toyota and Ford. This introduced a major new supplier to the market, triggering a price war in an already intensely competitive Chinese EV market, where reports suggest a new model is launched every 2 days. This competition is driving further innovation as manufacturers seek differentiation. LMFP, lithium manganese iron phosphate, adds manganese to achieve higher energy density than standard LFP. Double firing processes improve particle uniformity and performance by firing precursors at a lower temperature first, then milling and carbon coating the particles before a second firing. These innovations are delivering better performance for long-range, fast-charging EVs while maintaining LFP's cost and safety advantages. A significant factor in the lithium-ion battery price crash has been the parallel crash in raw materials prices since 2022. With 70 to 80% of a battery cell's cost coming from materials and 80% of that from iron phosphate and lithium for LFP batteries, these price reductions have been critical. In 2023, new lithium sources came online in Australia, Chile, and Argentina, reversing the 2022 lithium shortage and causing prices to crash. Some mines are now operating at a loss, but their Chinese operators are injecting cash to keep them open for strategic reasons. Iron ore prices have also fallen due to China's real estate crisis, which has reduced demand for crude steel production. Iron ore prices fell 15% in 2024 alone. These raw material price drops have allowed Chinese battery manufacturers to cut prices while still maintaining profitability. CATL, for example, saw revenues decline 9% in 2024, from 400 billion RMB to 362 billion RMB. But their gross profit margins increased from 19.2% to 24.4%. The LFP battery price crash is having significant effects beyond EVs, particularly in utility-scale energy storage systems that store power from renewable sources during low-demand periods. Traditional energy storage methods include pump storage using reservoirs on hills, power to gas using electrolysis to split water into hydrogen, then combining with captured CO2 to create methane. However, the plummeting cost of LFP batteries has made battery energy storage systems, BESS, increasingly competitive. LFPs were already favored for BESS due to their lower material costs and better thermal stability, but the Chinese EV boom since 2021 has dramatically accelerated their adoption. While BESS currently only provide 1 to 2 hours of power compared to 4 to 12 hours from pump storage, they're incredibly cost-effective and simple to deploy, often arriving in standard shipping containers, ready for installation. The United States is seeing massive investment in BESS projects, particularly in California and Texas, with $11.45 billion invested in the first half of 2024 alone. This funding is coming not just from government sources, but also from banks and infrastructure hedge funds. Looking ahead, the Chinese battery industry continues to advance, though LFP price reductions will likely slow compared to previous years. One of the most interesting developments to watch is sodium-ion battery technology. Companies like CATL, BYD, and Huawei are all actively developing this technology. While sodium-ion batteries currently have lower energy density than lithium-ion, they offer significant advantages. Sodium is far more abundant and accessible than lithium. They can potentially charge faster. Energy density is continuously improving. Given how optimized the LFP supply chain has become, it remains to be seen whether sodium-ion will make a significant impact, but it represents another potentially disruptive technology on the horizon. Conclusion: the LFP battery revolution, driven by Chinese innovation and manufacturing scale, has fundamentally changed the economics of electric vehicles and energy storage. Through creative engineering solutions like the cell-to-pack architecture, Chinese manufacturers have overcome what were once thought to be insurmountable limitations in LFP chemistry. The resulting price drops are making EVs more affordable and accelerating the transition to renewable energy by providing cost-effective storage solutions. As these technologies continue to evolve and prices continue to fall, we can expect to see even more dramatic changes in our energy landscape. Thank you for watching. Drop your comment below and follow me for more such content.